when this one is 1, 0, and then as this increases, transmission loss increase like this. If I plot this in log, and I can say that if this one increase 1 octave, meaning twice bigger than before, then this one increase. Log 2 is 0.3, therefore this is a 6 dB. So I can say increasing mass or frequency would increase the transmission loss 6 dB. Wow. That means the transmission loss is 10 dB, then transmission loss is 16 dB. Because I increase, believe it or not, the frequency twice bigger than. Yeah? Right. Okay. Now, important point is this. When omega m2z0 is 1, okay, omega is 2 pi f m over 2z0 is 1. This goes away. And z0 is a characteristic impedance of air. And what is it? Characteristic impedance of air. Characteristic impedance of air. Characteristic impedance. Anybody knows? 415. Okay, magic number. So that is a 415. And pi is 3 because we are handling dB scale, and 3 and 3 1.4 does not has many different. So 3 and Fm equal 1, and that is 3 divided by 401 is approximately 1, 3, 4, right? Okay, that is 134 and 130, 131. It does not make big difference, but let's mimic this number as, to the wall that look like this wall, and I want to put 3 over here. That is 131. So I might say the frequency is equal to 131 divided by m. This is the frequency over here that I call is blocked frequency. Okay? In fact, this is 134, right? Okay? 134? Huh? 2? Okay. So this is blocked frequency, and m is mass per unit area. Okay. Now, what is mass per unit area? Oh, this is too big. Mass per unit area of this. Mass per unit area. Okay. Suppose we have something that has mass per unit area is 10 kilo. 10 kilo. Okay? Then the blocked frequency is 13 hertz. So this is 13. And I want to control noise that has a frequency 1 kilohertz. And that has 100 dB SPL. That emits 100 dB dB sound. 13 twice is 26, twice is 52, twice is 100, 200, 400, 800. So I had 6 times 6 dB increase, so I have a 36 dB transmission loss. Therefore, if I use that as a input word to control sound, then the sound will be cutted by 36, at least 36 dB. Therefore, the sound I will get is 100 minus 36 dB. That is 64 dB down. If I want to reduce the sound more 6 dB, then what I can do? I double the thickness of the wall, because that makes M to be 2M, and 2 increase transmission loss of 6 dB, and this is called Mass law. This is Mass law. This is very well known and popular Mass law. Okay? Very simple result, but very useful. Mass law. What you remember, the magic number 132. Then you can get blocked frequency, and then you can estimate how much transmission loss we will get. Not using computer, you just use 132, and then what you need is your fingers. 132, 13, 26, 52, 100, 200, 400, 800. Okay. Oh, okay. 26, 52, 100, 200, 400. Yeah, right. 36 dB. Okay, let's summarize what we learned today. We start with a very simple case, plane wave case, but the assumption that has to do with the plane wave is not just asking us to handle very flat surface, but what we get using that assumption can be applied to the surface whose irregularity, typical size of irregularity is much, much smaller than wavelengths. In this case, we can assume the surface of this continuity is locally reacting, and we can use that result. Okay? And then we apply the boundary condition, pressure and velocity boundary, the continuity boundary condition, and we get famous Mass law. Simply says that increasing 1 octave frequency would increase 6 dB transmission loss. And typical or representative measure that dictate or characterize the transmission loss of limp wall is omega m. And that's why we call this result as a Mass law. Mass law. Mass law in acoustics is different with the Mass law that is used in other fields. Okay? So, in one word, the conclusion or summary of today's lecture is Mass law. 6 dB per octave increase. Okay? Thank you.